about what's coming up and stuff, and then if you have any homework questions, I can answer those. So first of all, we have the lab test on Thursday. The 23rd, I think. Yeah. And that'll cover all the stuff in labs 1 through 4. You know how I spent my birthday? Grading. Yeah. Anybody have any questions about any of the first 4 labs or anything about the lab exam?
Oh, yeah, I was wondering, was it lab 2 where we had like a huge data set with like this spreadsheet?
Yeah.
How is that?
Okay, so there will probably be 1 or 2 questions on that. And what I want you to remember is just the basic trends. And so not about the method or anything in that one, but just like what did we find. So if you remember what we found, so that was the one where we used a spreadsheet to calculate you know, how long it would take an object to fall a certain distance without air resistance and then with air resistance, and you could compare and just see in each specific case how much air resistance would affect the amount of time it took. And let's see, what we found was first of all, when we changed the masses, we did objects that were as dense, had the density of like steel, or I guess lead was the one we did, and then aluminum, and then cork. Okay, so things that were the same size, but the mass was less and less. And when we dropped those from 1 meter, even the difference between lead and cork, air resistance didn't really change anything, right? So lead, aluminum, cork, when we dropped it from 1 meter, there was essentially no air resistance effect. All 3 of those objects would have hit the ground at the same time. And then those 3 things, when we dropped it from 10 meters, it still was a very minimal air resistance difference between the lead and the aluminum. The cork was a little bigger, but I think it was still pretty small. I don't remember exactly what it was. Maybe it was like a 4% difference or something for the cork. There was essentially no air resistance effect for the 2 metals. And there was less than a 5% difference for cork. So even dropping them from 10 meters, there just wasn't much effect. And then the next thing we did was we kept the mass the same and changed the surface area, the radius of the sphere. And what we found was I think the two sizes were like a tennis ball. So we talked about an object that had a mass of 1 kilogram. And it was a tennis ball size compared to a basketball size. And when we dropped it from 1 meter, there was basically no air resistance effect. When we dropped it from 10 meters, I think there was about a 10% difference. That was the biggest difference we saw in the whole lab. So if you had to sum up all the results in one sentence, the most basic result from the lab was dropping things from 1 meter, 10 meters, air resistance didn't have that much of an effect. It probably had less of an effect than you would have guessed going into it. Other than that, there are some, some little differences you could notice. But basically, I think it's all like the questions I'm going to ask are going to boil down to the fact that there wasn't much difference for those. Like you have to get things to a higher speed than that if you're going to make those kind of changes in density, those kind of changes in radius, in order to see a big difference in due to air resistance. Any questions about that particular thing? Okay, so that's kind of lab 2 in a nutshell. Any other questions about the lab test? All right, well, these lab tests are sort of funny. I mean, they're just going to be, you're going to sit in your seats there and take this test on paper. It's not going to be a lab or anything, but it's going to be the kind of problems that you did in the labs. Besides lab 2, all the other ones were pretty much doing calculations or drawing figures, and you'll just have to reproduce that kind of stuff. Okay, any homework questions? I'd be happy to go through a couple of homework problems. Yep. Okay. Do you have the problem with you? Okay, anybody? I can look it up. This is particle kinetics. Okay, so 8. A car is accelerating backwards. It gives you the acceleration of the car, and a coffee cup falls. What acceleration would the coffee cup have according to the person driving the car? What would it look like? First, what would its acceleration look like to someone outside the car? So somebody's like looking at this thing going by as the coffee cup falls. They measured it or they videotaped it. What would it look like the cup and the fluid in the cup was doing? And second, what would it look like to the person inside the car? And then third, which of those is suitable for using Newton's second law? So those are two different measures of acceleration. Right? There's the person on the street sees an acceleration. The person in the car sees an acceleration. Only one of those is acceptable for using in F equals ma. And then the last one is calculate the net force. Okay, so the car is accelerating backwards at 4 meters per second squared. Okay, so number 8, particle kinetics. Okay, so a car is going this way. So let's say this is the positive direction. You know, usually this would be the positive x direction. And it says that the acceleration of the car is -4. So is the car speeding up or slowing down?
Slowing down.
Right, so so this car slams on the brakes. The acceleration is this way at 4 meters per second squared. Inside here, you know, there's a coffee cup that falls off the whatever, the dashboard or whatever. So part A. What's the acceleration observed by a camera on the ground? You know, outside the car. And anything in free fall to a camera that's fixed to the ground, the acceleration is just down at 9.81 meters per second squared. So acceleration of the cup relative to the ground is just 0, -9.81 meters per second squared. So now, what's the acceleration observed by a camera in the car? The relative motion equation says acceleration of the cup relative to the ground is equal to the acceleration of the cup relative to the car plus the acceleration of the car relative to the ground. So 0, -9.81 is equal to the acceleration of the cup relative to the car plus the acceleration of the car relative to the ground. This acceleration was given. It's 4 meters per second squared in the negative x direction. So this is just -4, 0. And so the acceleration of the cup relative to the car, just do the algebra. You can add +4, 0 to both sides, and you get 0, -9.81 plus 4, 0. And so you get 4, -9.81. So what that says is to somebody in the car, if they watch the coffee cup, that would be a weird thing to do, to just watch this coffee cup while you're slamming on the brakes, but it looks like it's falling, but it also looks like it's accelerating forwards. Does that make sense with your experience? If you slam on the brakes, it feels, you slam on the brakes and your friend in the back hits their head on the dashboard, Now, which of these two coordinate systems is suitable for Newton's second law? Newton's second law says F net is equal to the mass times the acceleration. But A and B give two different accelerations. So which one of those, only one of those can make sense in that equation. You can't have two different net forces. So which one of those is good? You have to use inertial coordinate systems. It's called an inertial coordinate system. It doesn't work with coordinate systems that aren't inertial. So what that means is if the coordinate system, and you can think of that as the camera, is accelerating or rotating, you can't use its acceleration in Newton's second law. Exclamation point. Okay, so which one of those two cameras is accelerating or rotating? The one on the street, the one that's on a tripod on the street, or the one that's mounted to the car? Car. The car is accelerating. I told you what that acceleration is. And so the camera that you use inside the car, you can't use that data for Newton's second law. And so this acceleration of the cup relative to the car, that's no good for Newton's second law. The acceleration of the cup relative to the ground, that is good for Newton's second law. Well, actually, we'll talk about this a little more when we talk about gravitation. But it turns out a camera that's mounted to the ground isn't an inertial coordinate system either, because, the Earth is rotating and hurtling through space. But the speed that it's rotating is really slow. So people are capable of, putting together careful enough measurement equipment that you can tell that the Earth is accelerating. But for most measurements, it's close enough to being an inertial coordinate system that we can use it. Anything that we do in this class, it's a good enough approximation that we're going to assume that if you put a camera on the ground, it's an inertial coordinate system. Okay, so like, for example, when we did that free fall experiment, you can think of that, that sort of elaborate setup we used where the two wires were burning a little mark in the paper as it fell. Well, that's all happening. You can think of that as sort of a crude camera that we devised that's connected to the Earth, connected to the ground. Those results were good enough for us because our, the error in our measurements was a lot worse than the non-inertial coordinate system that comes from the Earth rotating. And then part D. Okay, so then use Newton's second law to calculate the net force on the coffee cup. Well, this is going to be sort of underwhelming. So the net force is equal to the mass of the coffee cup times the acceleration of the coffee cup in an inertial coordinate system. So that's 0, negative 9.81. Or we can write that as m times 0, negative g. And so the net force is just equal to 0, negative mg. So the only force on the coffee cup is the weight. Sometimes, okay, so there are some cases where it's useful to measure what forces it appears like are happening. These are like fictitious forces that, so to somebody inside the car, it would look like there's a force acting on the coffee cup, accelerating it forward. And sometimes you hear people talk about that stuff. I think really you hear about those kind of things more often than you should, just because this is sort of a boring way to think about it. It's more fun to think that there's this this imaginary force making this thing accelerate, you know. But this is really the true story. You find a coordinate system that's inertial, that's not accelerating. You measure the acceleration in that coordinate system, and then use that to give you the true forces acting on the thing. So just one more thing about those fictitious forces. The main fictitious force that people talk about is called centrifugal force. Have you ever heard that word before? People talk about that more than they talk about centripetal acceleration or centripetal force. In circular motion, the true force is centripetal. There's an acceleration. If you're moving in a circle, you're accelerating towards the center. That's the centripetal acceleration. And so there always has to be some force pushing you towards the center. When people talk about centrifugal force, they're talking about what it feels like is happening. And like if you're on one of those things at Valley Fair or whatever, you know, it's spinning around and pressing you up against the wall, it feels to you like there's a force pushing you against the wall, right? The reason it feels like that to you is because your brain is, and your eyes are a non-inertial coordinate system. What's really happening is not that you're being pushed into the fence behind you, that, you know, it's that fence behind you is pushing you this way to make you keep moving in a circle. It's applying that centripetal acceleration. So when people talk about fictitious forces and stuff, just the bottom line is like, just be like, I don't deal with those. Okay, that's a waste of my time. I tell you what really happens. Any questions about that problem? Yes. If it's what? If the centripetal force is removed. Mm-hmm. Yeah. Yeah. Okay, so if you're spinning something around on a string and then the string breaks, what the thing on the end of the string, what it does is it just takes off with a constant velocity in exactly, you know, with exactly the constant velocity that it had before the string broke. And that's according to Newton's second law too. You know, if acceleration is a measure of the change in velocity. And so if that string is the thing providing the force that's keeping it moving in a circular motion, if all of a sudden that F net disappears, then the acceleration disappears, which means that the thing now just maintains a constant velocity. It can't accelerate anymore. So really it's just all of a sudden, what happens when that string breaks is all of a sudden the thing that's causing the acceleration disappears and there's no more acceleration. Any other questions? Any other homework questions? Okay. Okay. Yes. Okay, so in this one, we're given the force vector as a function of time, and we're just asked to figure out the position vector as a function of time. It doesn't tell us the mass. Okay, and the function is t negative 3t. Okay, so the force as a function of time is t negative 3t, is that what I said? And since it doesn't give a mass, we'll say the mass is m. Well, Newton's second law says, and this is the net force, it says, I believe. Yeah, the net force. So F net is equal to this at any time. So Newton's second law says t negative 3t, that's F net, is equal to the mass times the acceleration. I'll break it up into x and y components as functions of time. And so the acceleration vector as a function of time, you can solve those two equations just one by one, is t over m for the x component and negative 3t over m for the y component. So that's the acceleration. Any questions about that part? So if you're given acceleration as a function of time, you can use Newton's second law to calculate net force as a function of time. If you're given net force as a function of time, you can use Newton's second law to calculate acceleration as a function of time. And then from there, it also tells us that its position and velocity are 0 at time 0. So v of 0 is the 0 vector, and p of 0 is the 0 vector. And now we're just going to do the differential equation, integrate the acceleration to get the position. The velocity is the integral of the acceleration. So, you know, velocity is a function of time, is the integral of the acceleration with respect to time. So that's t squared over 2m plus c1. And negative 3t squared over 2m plus c2. That's the velocity vector. And we can figure out these constants c1 and c2 from the fact that the velocity is equal to the 0 vector when time is equal to 0. So the 0 vector is equal to 0 squared over 2m plus c1, and negative 3 times 0 squared over 2m plus c2. That means c1 and c2 have to be 0. So the velocity vector as a function of time is t squared over 2m negative 3t squared over 2m. Any questions about that first step? And we just do that one more time to get the position. The position vector as a function of time is the integral of the velocity vector as a function of time with respect to time. And so we get t cubed over 6m plus c3 and then negative t cubed over 2m plus c4 . The zero vector is equal to 0 cubed over 6m plus c3. And then the y component is negative 0 cubed over 2m plus c4. That says c3 and c4 are equal to 0. So the position vector is t cubed over 6m negative t cubed over 2m. Any questions about that? Okay, so remember that if you're ever given acceleration as a function of time or f net as a function of time, you can calculate the other one using Newton's second law. And then once you have acceleration as a function of time, you can use those derivative relationships to figure out velocity as a function of time, position as a function of time. I was late posting the solutions to particle kinematics in 2D. I sort of forgot about that. But those are up now, and the solutions to particle kinetics are up. Not all of them, but a lot of them. So that should help look for those as you're working through this. Any other questions about the homework? All right. So back to the 5 types of forces with known directions. These are, the first one is the weight. That's the easiest one. The second one is pushing contact. The third one is pulling contact. Usually, but not always, this involves cables, strings, and ropes. The fourth one is friction. And the fifth one is springs. Who remembers why we deal with springs? Yeah, that's right. Yep. So in a lot of branches of engineering, like branches of mechanical engineering, aerospace engineering, civil engineering especially, you deal with the elasticity of engineering materials. And springs are kind of an introduction, not kind of, springs are your first glimpse at dealing with this idea of elasticity. What elasticity means is if you apply a load to something, it deforms. And as soon as that load is gone, the deformation disappears. Want to hear something funny about elasticity? Elasticity is an approximation. Nothing deforms instantly as you apply a force to it, or returns to its original shape immediately when you remove a force from it. Relativity, Einstein's relativity, is based on the idea that no signal of any kind can move faster than the speed of light. So what any kind of elastic theory says, if you apply a force to something, in a sense, you could think of applying a force to this end as sending a signal to the person on the other end. As that thing deforms, they're getting that signal. And so if applying a force causes an instant deformation at a distance, it violates the idea that the speed of light is sort of like a speed limit of things. So that's another, like if you're ever, talking to someone you want to impress and they say something about elasticity, you can be like, that's just an approximation. That violates the theory of relativity, dummy. And, saying that kind of stuff, it makes people know, oh, like they're really smart. And then, so it's a good thing to do. Okay, so which of these have we done so far? We did weight. We did pushing. Yep, we're done with that now. So now we're on to pulling contact and cables. So pulling, usually with cables. So for example, the kind of problem that we'll see is if you have one cart rolling along the ground, connected by a cable to another cart. And then you apply a 50 Newton force here. Then, for example, what's the force the cable applies to cart 1? Okay, and the rules for a pulling contact. So the pulling force direction is parallel to the cable. And away from the chosen body. One way to always get this right that I think is helpful a lot of times in really complicated problems is to, you can sort of imagine when you choose the body to isolate, imagine including just a tiny little bit of that cable that's connected to it. So you can include a tiny bit of cable in the chosen body. and then the force applied by the cable acts straight out of, I'll call it the stump, a little tiny piece of cable, straight out of the stump. Okay, so let me show you a picture of what I mean. So for example, if your chosen body, let me draw this setup that I had before again. So there's cart 1. Cart 2. 50 newtons. Okay, so if we're going to isolate body 1, there's the outline. I'm going to include just a little bit of that cable on the end. There's the weight acting. There's a pushing contact from the floor. I'll call that normal 1. And then the only other force is the pulling contact from the cable, and that acts straight out of the stump, parallel to the cable, away from the chosen body. And I'll label the magnitude of that force T for tension. And a free body diagram of cart 2. There's the weight of that cart, M2G, pushing contact from the ground, I'll call that N2. There's the applied force, 50 newtons. And now the pulling force acting on this cart goes straight out of this stump, that way. And since this is the same cable, the magnitude of that force has to be the same. So this is the same magnitude. We're going to use the same variable label for it because it's the same cable. Any questions about that? Okay, well, let me do an example problem. It's going to basically look just like that one. Let's say that this cart on the left has a mass of 5 kilograms and is connected to a 2 kilogram cart. And there's a force of 20 newtons applied to the right. And we want to calculate first the acceleration of the system. And second, the force vector the cable applies to the 5 kilogram cart. All right, so to calculate the acceleration of the system, what do I want to isolate? This came up with last time with the pushing contact problems. I always isolated the same thing, first of all, if we wanted to calculate the acceleration. Like if we had a bunch of carts or boxes or something in a row, we did that kind of thing, right?
Just like one body.
Yeah. So what we want to do is we want to isolate both of the two things together.
Oh, okay.
So isolate the whole system together. To find the acceleration. So a free body diagram of the whole system. Looks something like this. So what loads are acting? What forces?
From the ground.
Let's go in order. So the weight first. That's 7 kilograms times 9.81. So that's 68.67 down. And then there's a contact force with the ground. I guess I'll break that up into two. So we'll say there's one force on this cart. I'll call that N5. And then one force on this one, I'll call that N2. Then there's the applied force of 20 newtons. Any other forces? There aren't any because the cable is applying a force to this and a force to this, but that's not something happening to the boundary. We've gotten that out of the problem by putting those forces all inside what we're isolating. But that's sort of an example of why it's so important to draw an outline with no internal details or whatever, to just be clear about what are the forces applied by the outside world and what are the things that are just totally internal. So Newton's second law says 0 N5, that's in the positive y direction, plus 0 N2, plus 0 negative 68.67, plus 20. That's the net force, and that's equal to the mass times the acceleration. The total mass is 7. Do we know anything about the acceleration? We do know one thing, and this is something, in order to solve a problem like this, you're going to always have to recognize this, and it'll come up in a lot of these problems. This thing is just rolling along a surface, right? So it's not going to jump, and it's not going to sink. So all of the motion is just happening along the x-axis, and we don't have to guess about whether it's going to accelerate to the whatever that is, left or right. All we have to do is say it's going to be in the x-axis. We'll assume that it's in the positive direction, and it'll give us a negative number if it's in the negative direction. But we do have to say there's only going to be an x component. So I'm going to write the acceleration as a0. Okay, this gives two equations. The x equation says 0 plus 0 plus 0 plus 20 is equal to 7a. And the y equation says n5 plus n2 minus 68.67 is equal to 0? Well, we're trying to find the acceleration, so this one doesn't help us. That would let us calculate those two pushing forces. But this one says the acceleration, well, A is equal to 20/7, is about 2.857. Meters per second squared. Okay, now that is not really an acceleration. That's just a variable. So how do we figure out the acceleration vector from that variable? So Newton's second law holds all this stuff in it in vector form. That's the acceleration. We just didn't know yet what A was. Now that we have A, we can plug it in there. And so the acceleration vector is positive 2.8570. And all of this stuff is moving together, so that's the acceleration of the 5 kilogram cart, and it's the acceleration of the rope, and it's the acceleration of the 2 kilogram cart. Okay. That wouldn't necessarily be true if that cable was extensible, you know, like if it was really stretchy, this one can start to accelerate before this one feels much. But anytime we're talking about cables, that's going to be the situation. So what do we want to find next? Part B, we want to find the force vector the cable applies to the 5 kilogram cart. So now this is where the pulling contact is going to come into it. So what do we want to isolate? The 5 kilogram cart or the 2 kilogram cart? The 5 would make more sense. After I do this, I'm going to show you that we get the same answer if we isolate the 2 kilogram cart. But a free body diagram of the 5 looks like this. You have the weight of 5 times 9.81, 49.05. You have the pushing contact, N5. You have the pulling force straight out of the stump with a magnitude T. Newton's second law says T0 plus 0, negative 49.05 plus 0, positive N5 is equal to the mass of what we're isolating. What's that? 5. Times the acceleration of what we're isolating. What's that? That's what we just solved for. Yep. 2.8570. So we get two equations. The x equation says T plus 0 is equal to 5 times 2.857, 14.285. The y equation says negative 49.05 plus N5 is equal to 0. This one, it's a perfectly good equation, but it doesn't help us with what we're trying to find, so forget that one. This one tells us that T is equal to 14.285 newtons. So that's basically it. That's the magnitude of the force, but we're asked for the force vector applied to the 5 kilogram. So how do we go from the value of t to the force vector applied to the 5? It works just like the acceleration. This is the force on the 5 by the cable. So now we just have to take this t value and plug it in there. So the force on the 5 by the cable is equal to 14.2850. Any questions about that? Okay, so let's now isolate the, so we're done with it, we did it. But now let's see what happens if we would have isolated the 2 kilogram box. Okay, so the free body diagram of the 2. There's the little bit of cable. There's a weight of 2 times 9.81, so 19.62. There's the normal force of the 2. There's the external load of 20. And there's the cable tension T going that way. So Newton's second law says negative T 0 plus 0 negative 19.62 plus 0 N2 plus 20 0 is equal to the mass 2 times the acceleration 2.8570. So we get an x equation that says negative t plus 0 plus 0 plus 20 is equal to, what's 2 times 2.857? 5.714. I don't know if that's, I bet 50% of those digits are right. It's important though, actually. So someone calculate that, please. Okay. Yay! Okay, and then the y equation says negative 19.62 plus N2 is equal to 0. This one doesn't help just for what we're trying to find. This one says P is equal to 20 minus 5.714. So what's 20 minus 5.714? 14.28. It is 6. Okay. So now, well, this doesn't give us the vector that the cable applies to the 5 kilogram box. We could use it to find the. Okay. Well, what if we wanted the force vector applied to the 2 kilogram box first? This is the force on the 2 by the cable. And so we just plug this in here. The force vector on the 2 by the cable is negative 14.2860. See how that negative came in there? All right, so now I want you to notice something really kind of surprising, cool about this. There's one digit wrong. We took this to 3 digits, okay, to 3 decimal places, and there was round off error of 1/1000th. But you can probably believe these are the same. Okay, so with this free body diagram, where is it? With this free body diagram, okay, where the mass was different, there was no 20 Newton force, we've somehow figured out the same tension for that cable that we did with this free body diagram, where the tension's going the other way, the mass is different, the force is there. It's amazing, right? It's like magic. Like this one, that 20 Newton force is there, but this one, like, how did it know? But do you know how does it know? What? Well, the reason that it knows is that when we did that first step of calculating the acceleration of the 2 carts, that acceleration encloses a lot of information. You know what I mean? And so then when we plugged that acceleration into the other 2, it gave the extra bit of information that doesn't show up in that free body diagram. But it's cool how that works, I think. With these kind of problems where you have multiple bodies in contact like this, there's always a bunch of ways to go about it. And if you follow the steps correctly, you'll get the same thing. Okay. I have a question before I go on. Did I do a problem like this? I guess I can just look. Oh yeah, okay, I did. So the next thing that we have to include is pulleys. And all pulleys do and by the way, I'm talking here about massless and frictionless pulleys. Which ends up being a perfectly fine assumption in a lot of cases. All a pulley does is change the direction of force that a cable applies. It doesn't change the magnitude of the force. And I know when I first saw pulleys in a physics class, that confused me. I don't know if I don't know if it's the same for you. It doesn't change the magnitude. But I remembered being told that pulleys were one of these, some small number of like simple machines, and that you can use pulleys to reduce the amount of force that's required to like lift an object. Okay, And so then when I started working through this stuff, I was like, well, that doesn't make sense. Does it change the magnitude of force you need to apply, or doesn't it, you know? And the answer is a single pulley doesn't change the magnitude of the force. There is sort of a smart way you can rig up a set of pulleys that does allow you to change the magnitude of the force, but it's not really the pulley that does it, it's the configuration. And so I'll talk about that. Okay? But like if you have a single pulley, so let's say you have a pulley attached to the ceiling, and you have a 10 kilogram mass there, and let's say you want to figure out the force required to hold this up. So what's the force F required, so that the way I'm going to say this, holding it up, is I'm going to say there's no acceleration. So the mass has no acceleration. Well, the way this works is I'll draw a free body diagram of the mass. The tension stays the same all the way through this cable. So I'm just going to call this force F. We have the weight of 10 times 9.81, so 98.1. And Newton's second law says 0F plus 0 negative 9.81 is equal to 10 times the 0 vector, because it's not accelerating. And so the y equation says F is equal to, no, I just wrote that number in wrong. That weight is 98.1. So F is equal to 98.1 newtons. And so what that says is the force you have to apply to this cable after it goes over the pulley to hold this up is exactly the same force that you would just have to pull up to hold this thing in the air. The only thing that happened is now you're applying that force in the opposite direction. So the pulley changed the force direction, not magnitude.
I was just wondering if you know, like, how setting up like multiple makes it, like, does it, like, how that works?
Yeah, I mean, we'll do some calculations like that, but the basic way it works is something has to take that force, and you're rigging it up in a way that the ceiling takes some of the force, you know. But we'll do calculations like that. It's really cool, and when you first do the calculation, it looks like a trick, like something must be wrong. But actually, we have pulleys in the lab. Let's do it on Friday. It only takes a couple minutes. Rig up a couple of pulleys in the right way, and the force that's required to hold up a 5 kilogram mass or something, you can feel it's half as much. And if you rig up more pulleys that way, you can make it lighter and lighter. It's really cool. Okay, so let's do another example. So let's say, again, we have a pulley hanging from the ceiling and a 10 kilogram mass over here. And a 5 kilogram mass here. And we want to know what are the cable tension and the acceleration of the 5 kilogram mass. Okay, so first I'm going to isolate, draw a free body diagram of the 5 kilogram mass. The weight is 49.05. What else is touching this?
The cable.
The cable, yep. So that's right out of the stump with a magnitude T. We don't know what that is yet. And so Newton's second law says 0 positive T plus 0 negative 49.05 is equal to 5 times. And now we have to think about what we know about the acceleration. How is this system going to accelerate? Well, everything is just happening vertically, right? So this thing, its height is just going to change. If we think about it a little bit, we happen to be able to tell that it's going to accelerate up. But just like with the rolling carts, we knew that the acceleration was only going to be in the x direction. With this, we know the acceleration is only going to be in the y direction. We're going to use that. So this is 0. I'll call this A5. Okay. This gives two equations. The first one says 0 equals 0, so obviously that one is useless. But the y equation says T minus 49.05 is equal to 5A5. So this is a good equation. But we can't solve it yet because, this is one equation with two variables. Okay, we're going to just set this aside. We'll come back to it later. But our goal is to come up with a system of equations that we can solve, where we have as many equations as we have unknowns. So we need the same number of equations and variables. So now we'll go to the 10 kilogram. There's a weight, 10 times 9.81. There's a force from the cable. What's the magnitude of this?
T.
T, yep. We know that that's the same force as that cable applies to the other mass. And so Newton's second law says 0t plus 0 negative 98.1 is equal to the mass. And what do we know about this acceleration? The acceleration of the 10 kilogram. Well, this is also going to be vertical, right? So I'm going to call this 0a10. Turns out there's something else that we're going to know, but we can leave it like this for now, okay? The x equation says 0 equals 0, so nothing there. The y equation says t minus 98.1 is equal to 10a10. Okay, so now we have a system of equations. So now there are two boxed equations. How many variables do they have? 1, 2. This one has t, so that's not a new variable, but this is a new variable. So we have two boxed equations, 3 variables. So we need one more equation. We need, we need one more equation relating these variables in some way. And an equation like that is called a constraint equation. Okay, so our three variables are t, the acceleration of the 5, and the acceleration of the 10. Look at this system, original system. Is there anything are there any relationships that you can see between tension and or that acceleration and or that acceleration? There's one geometric relationship. That is, think of it this way. What happens if you move the 10 kilogram box down an inch? What happens to the 5 kilogram box?
Goes up an inch.
Up an inch, right? And so what happens if this is moving in the negative direction at 5 meters per second? What's the velocity of this? Positive 5 meters per second. And so if this has a downward acceleration of 1 meter per second squared, what's the acceleration of this? If this is down at 1 meter per second squared, and this is up at 1 meter per second squared. Our constraint equation is going to say that which one do we want? The 5? The acceleration of the 5?
Yeah.
So our constraint equation is going to say that the acceleration of the 10 is the negative of the acceleration of the 5. So A10 is equal to negative A5. So our new 3 equation system says our first equation, where is it? Our first equation says t minus 49.05 is equal to 5a5. Our second one says t minus 98.1 is equal to 10a10. And our third one says A10 is equal to negative A5. That's 3 equations for 3 variables. And you can just solve that by substitution. We'll put negative A5 in for A10. So this is going to give us T minus 49.05 is equal to 5A5. The second one says T minus 98.1. I'll substitute in equation 3, and that gives us negative 10A5. And then I'll subtract these 2 equations, and you get positive 49.05 is equal to 15A5. And so A5 is equal to, what's 49.05 divided by 15? 3.27? 3.27 meters per second squared. And if we want the acceleration vector of one of those 2 boxes, if we want the acceleration vector of the 5 kilogram box, we can plug that back into the acceleration vector we used in Newton's second law. So the acceleration vector of the 5, if you plug that back in, is 0, 3.27. And now what about the tension? Yeah, now you can just plug that in for, so yeah, either one of these 2 equations will work. Plug it back for T. So we get T minus 49.05 is equal to 5 times 3.27. And what do you get for T?
I got 65.4.
65.4 newtons. One thing that's interesting about that is in the example I did right before, where you just have where you're just holding up a 10 kilogram mass, the force, the tension in the cable was 98.1 newtons. Once you allow this thing to accelerate, that force changes. So you might look at that and think like, oh, well, the tension in the cable is going to be the weight of one of those 2 masses. But it wasn't. It was actually like somewhere in between the weights of those 2 masses. So that acceleration messes up some things about your intuition of what's going to come out. Let's do one more example. So this time, let's say the pulley is on the corner of like a ledge, and there's a cart here, and then a mass here. let's say that rolling cart is 5 kilograms, mass is 2 kilograms, and we want to know what's the acceleration vector of the 5 kilogram cart. Okay, so the weight of that 2 kilogram mass is gonna make it ascend, and it's gonna pull the 5 kilogram cart over towards the ledge. And we want to see what the acceleration is going to be. The basic idea of this is pretty similar to the last example. It's just going to be a slightly different constraint equation. So a free body diagram of the 5 kilogram. We have a weight of 5 times 9.81. A normal force, I'll call it N5. And then the only other force is the cable force. So Newton's second law says T0 plus 0 N5 plus 0 negative 49.05 is equal to, what do we know about the acceleration of the 5 kilogram? It's horizontal. And that's all we need to know. We're not gonna, even though it's easy to guess which direction it's gonna be, we don't care about that. We're gonna assume it's in the positive x direction. All we care about is that it doesn't have any y component. So this is equal to 5 times a5 for x and 0 for y. So we get an x equation that says t is equal to 5 a5, and a y equation that gives us some stuff, but it's nothing that's useful for what we're trying to solve. So we don't care about this one. We do care about this one. We can't use that to solve for anything yet because it's one variable with 2 equations, but we'll come back to that as a system. And then a free body diagram of the 2 kilogram, the hanging mass. We have the weight of 19.62. It's the same cable as before, so this is T. And Newton's second law says 0T plus 0 negative 19.62 is equal to the mass. What do we know about the acceleration of this body?
It's vertical.
Vertical, yep. So I'll write this as 0 A2. The x equation says 0 equals 0, so we know we can't use that. The y equation says t minus 19.62 is equal to 2a2. Okay, so we have 2 equations. How many variables? Yep. So we need one constraint equation. And so what's the constraint equation that makes sense here? I think the best way to think about these is always to just think, one of them goes an inch one way, where does the other one go? So if this one goes an inch in the positive x direction, where does this one go?
negative 1 is
Yep, an inch in the negative y direction. So it's a 1-to-1 relationship with that negative sign, and it, the 5 is in the x component, the 2 is in the y component. So our constraint equation says A5 is equal to negative A2, or I guess I'm going to write it the other way. A2 is equal to negative A5 because what we're trying to solve for is A5. So our system says T is equal to 5A5. The second one says T minus 19.62 is equal to 2A2. And I'll just make that no, I'll write it like this. Is equal to 2A2. And then our third one says A2 is equal to negative A5. Yep.
I was just wondering why we don't have to write A2 and negative 5 because
Okay. Right. Well, it's because these are just variables, and so
it just when we solve for that, just where to put it.
yeah, and then once we solve for those variables, we plug them back into the vectors. And so this says T is equal to 5A5. The second one says T minus 19.62 is equal to negative 2A5. And then I'll subtract these two. You get positive 19.62 is equal to 7A5. So A5 is 2.803 meters per second squared. And so now you can go back to Newton's second law for the 5 kilogram. Plug that number back in there, and you get that the acceleration vector of the 5 is equal to 2.8030 meters per second squared. And then if you wanted to calculate the tension from that, you could. Any questions about that? Okay, that's it for today. I have one thing to say. The last 2 classes, talking has gotten a little out of control for me. I can't concentrate when people are whispering so much. If you want to whisper like a question about what we're doing to each other, that's fine. But today it was just going on sort of constantly the whole time. So please don't do that. Okay. All right. See you Thursday. Lab test on Thursday.